try the, oh, wait, okay. Oh, no, yeah, I remember what we're going to do. We're going to do this in 2 steps so you can see how easy it is. We'll do it the hard way, and then we'll do it the easy way. Okay, let's see what this base 10 value is. All right, I have to remind myself of something. Bear with me for just a second. Okay, if we're converting this binary number to base 10, we need to remind ourselves of these place values. And it's a byte. It's 8 bits, so I'm going to have a lot of place values to represent here. Most of them are zeros, though. This 1, and then I've got, let me make sure, 1, 2, 3, 4, 5, 6 zeros. 2, 3, 4, 5, 6. Yeah, it's a byte of data. We know this is the ones place. If that glitch happened much more frequently, it would be a real problem, but fortunately it only happens about once per Nearpod. 1 times 1 is 1. I have 0 2s. I really don't need all these. I just need to know what they are. I know I have 0 of each of them. That's the 2 to the 3rds or the 8s place. That's the 16s place. That's the 32s place. That's the 64s place, which makes this the 128s place. 0, 1, 2, 3, 4, 5, 6, 7. That makes sense because 8 bits and 0 through 7 will be 8. Okay, so I have 128. That's 128. Whew. So I have 128 and 0 and 0 and 0. These are all zeros. 128 plus 1. So this is 129. All right, now I know that I didn't put this on your notes, but put this on your notes. Let's make that into base 16 now. Let's figure out the hexadecimal number that's equivalent to 129 in base 10. In hexadecimal, I have a ones place, I have a 16s place, and I know that's going to be plenty because we've had numbers in the 200s that I didn't need to go above the 16s place. So how many 16s do I need if I want to represent 129? 5 16s is 80, 6 16s is 96, 7 16s is 112, and 16 more is 128. Ooh. 8 16s is 128. 80 and 48, yep. 8 16s is 128. All right, and I just need one more for 129, so I need 1 1. 81, or it looks like 81 in hexadecimal. Now, every hexadecimal number doesn't have to have A's or E's or F's. I mean, you could have a 1 and an 8, 1 1 and 8 16s. Right now, here's the key. Here's the key to this whole idea of hexadecimal. You ready? Do you see this nibble? Isn't that 1? You see this nibble? By itself, wouldn't that be 8? 0 1s, 0 2s, 0 4s, but 1 8. So you can take each nibble and convert it to base 10 and represent that base 10 number with the hexadecimal value. Like if you get let's say you had a 1 0 1 1, you had an 8, a 2, and a 1. 8, a 2, and a 1 would be 11. You would represent that as a hexadecimal digit B. But you can do each nibble separately and take those 4 bits and represent them with a single digit. You can skip right over the base 10. You don't need to do all this. You go from here to here, from here to here. And if you do it all the time, like you can only imagine, if there are only 15 values you can hold in a nibble, people that working with computer programming just look at a string of 4 bits, a nibble, and just know the hexadecimal value without even having to think about it. It just becomes internalized. And so you can take those long strings of 1s and 0s and knock them down by a factor of 4 from a byte of 8 bits to a 2-digit hexadecimal code. And therein lies the efficiency of hexadecimal.